It's not boring.
This story is about working hard even when it seems silly,
It's not boring.
and for the people trying to make crazy things happen.
It's that shot of optimism, yeah. It's not boring.
Not boring is for the optimists.
It's that
Take a little shot of optimism. Take a little shot of optimism.
it's not boring.
Let's just zoom out and take a little shot of optimism.
It's not boring.
Happy Thursday and welcome to Not Boring Founders.
On Tuesday, I announced Not Boring Capital Fund 3 and talked about the fact that we want to fund hard startups that, if everything goes right, can bend the world's trajectory upwards. I also talked about the fact that we want to more tightly couple the types of companies that we're investing in Not Boring Capital with the media business that we run over here, the podcast, the newsletter. We want to tell the stories of those ambitious companies and give the founders of those companies a chance to tell the stories themselves. So for Not Boring Founders in 2023, expect to hear a lot of conversations with founders of hard startups who are trying to bend the world's trajectory upwards. Some of those conversations will be with portfolio founders. Some won't. Some will just be because we're interested in the space and we're still trying to learn what's going on there. And today is one of those conversations. Today, I'm talking to Nick Chadwick, the CEO and founder of Mission Zero Technologies. What Mission Zero does is really cool. It pulls carbon dioxide from the air, and then it sells that carbon dioxide to people who might need it to make chemicals or fizzy drinks or concrete or any number of things. Mission Zero is one of the recipients of an advanced market commitment from Frontier, the effort from companies like Stripe, Microsoft, Shopify, and more to make sure that there's a market for these really valuable carbon dioxide removal credits when companies like Mission Zero achieve what they're trying to achieve and pull carbon dioxide from the air. But one of the most interesting things about this conversation to me is the fact that Mission Zero is both taking advantage of the credits that it's going to generate, but it also believes that to long-term, sustainably and scalably pull carbon dioxide from the air, it needs to find a market of willing buyers to actually buy the CO2 that it pulls down. It's an example of a company taking a moonshot sci-fi bet, but with a practical business model. I loved getting to dig into the business behind CDR, the scale of the challenge, how we're going to pull gigatons and gigatons of CO2 from the atmosphere every single year, and how Mission Zero plans to attack that. And I hope you enjoy the conversation as well. Before we get to the conversation, though, a word from our sponsor, Causal. Many of us rely on Excel. I've written about it. I think Excel will never die, and we couldn't imagine a world without it. Excel lets us quickly crunch numbers, build financial forecasts, and model out scenarios to make better decisions. But modeling in Excel and G-Sheets does come with its challenges. Manual data dumps, refs, untraceable errors, and a lack of data protection create a constant stream of manual work, stress, and a lack of confidence in the work that you just did. That's where Causal comes in. Causal is a better way for working with numbers. It's like Excel minus the arcane formulas. No more sheet 1, exclamation point, $E, $4, or VLOOKUPs. Plus effortless modeling, live data integrations with accounting systems, CRMs, and more, and beautiful interactive dashboards. And given current market conditions, every startup needs a solid financial model to steer the ship. I've worked with the Causal team to create the Startup Suite, a set of 4 template models for early stage companies. It includes your revenue model, hiring plan, P&L, and runway projection, the basics for any startup to keep an eye on the finances and plan for the future. If you're a startup founder, early stage employee, or just a lover of all things data, you'll love Causal. We love Causal and the product so much that Not Boring Capital is an investor in the company, and we use it for our modeling over here at Not Boring. So you can use the Startup Suite as a starting point or sign up for the product for free. The links are in the description below. Go check it out and tell them that Not Boring sent you. And now, without further ado, please enjoy my conversation with Nick Chadwick, the founder and CEO of Mission Zero Technologies.
Nick, welcome to Not Boring Founders.
Thanks for having me. I'm really excited to be here.
This is going to be a fun one. As I was saying beforehand, I think direct air capture is one of the more just kind of fascinating concepts. The fact that you're just taking this problem out of the air and turning it into products that people can use. So really excited to dive in. I guess the best place to start is how you got here and how you ended up starting this company. Nadia Asparuva had this post on climate tribes and said that people are either incumbents or switchers. Which are you? Are you coming kind of from within climate and science, or are you coming from something else? And how'd you get here?
Some of them were both. So I'd say I'm an incumbent in that I'd always been working on climate change technologies and approaches to kind of fix the variety of problems climate change causes. So a focus on water was actually the majority of my work, essentially post my PhD. But switching into carbon capture happened about 6 years after that point. So um, the long and short story is that I'd been working in water for about 5 years. It's one of those things where people don't really give it the attention that it deserves. And so you can kind of, the carbon capture is just one of those areas where actually, like, if you're doing it right and you're doing well, you can make really big progress. Like it's a really high leverage activity actually. And so what you're always dealing with things where, you're mopping up the problem after the fact, so to speak. Whereas, carbon capture, like I'm literally removing CO2 from the atmosphere. Like it's as simple as that. I have this thing where I sort of wake up every day and I go, is it just because it feels good that it seems like it's a good idea? But, the more we like investigate it, the more we realize like this is actually a really sensible and good thing to do. And actually one of the only options we'll have available to us. So yeah. A little bit of both, kind of switch from water to carbon capture, but I've always been, I'm a scientist, material science by background. So yeah.
Makes a lot of sense. So for the people in the audience who are less familiar, just kind of with the space, could you give us just a high level overview of the carbon capture space, what the different approaches are, kind of when this whole movement got started, and just where we are today?
Yeah. So in carbon capture, you can basically break it down into traditionally kind of two subsets. So one is point source capture. That's probably the one that a lot of people will be familiar with. And this is where you're basically capturing like relatively high concentrations of CO2 from a flue stack and say a cement factory or a refinery of some kind. And so one of the arguments for point source capture is that there's a lot of CO2 to capture. And because it's so high concentration, it makes a lot of sense economically. But there's a lot of questions about deployment, whether it actually works. And if you're looking about projects that have been deployed in point source, it's not so clear that actually it makes a lot of sense. You're also very constrained about where you can work. So that's one of the main problems with it. But it is cheaper than the other subset of carbon capture, which is direct air capture. And so this is where you're literally removing CO2 from the atmosphere. And so, if we were to compare the concentrations of carbon dioxide in the two streams you'd be processing in point source versus direct air capture, you're talking 10%, maybe higher in point source capture. Sometimes, depending on the range, it can be like 90%. In direct air capture, it's the atmosphere, it's 400 ppm, it's 0.04% of the atmosphere. So it's inherently like a much more energy intensive process to do. I think there's a large amount of arguments around like, why would you do direct air capture? Because it's so energy intensive, or, you have to blow so much air, or you have to do so much of this. But there's kind of two things I'd say there, and that we don't really have a choice. I mean, it's clear from the IPCC and all these kinds of things that like we're going to have to do direct air capture, remove CO2 from the atmosphere. And also when you start interrogating the market dynamics of how you can make carbon capture from the atmosphere profitable, then actually it becomes really interesting. So despite this kind of misnomer of like, you're essentially telling entropy to leave kind of thing, because it's such an anti-utility test. Actually, when you start looking at implementation, it becomes incredibly interesting.
So we'll get to, I want to understand kind of all of the dynamics that go into just the business of direct air capture. First, so what's the mission zero approach? What are you building? What's the mission, and how's it different than other alternatives?
We're commercializing this technology that we believe solves many of the constraints in the deployment capture. So when we started the company, and this is before we'd actually spun it out, right? So we spent about 3 months at a venture builder, really doing a lot of like customer development work, understanding what the problems are. And we took this really cynical view that someone has to pay for it, right? It's kind of view of like, climate change is existential,
Yeah.
and ultimately someone's going to have to pay for it. right? Now, I think the prevailing view essentially is that governments will come in and regulate, and the voluntary carbon credit market will set itself up, and there'll be established rules for everyone in a variety of jurisdictions, et cetera, et cetera. But actually, to get to the point where that makes sense, it's not realistic at this moment in time. It's not necessarily the case. It's good that we have buyers like Stripe is one of the largest buyers of carbon removal on the planet. It's good that they're taking those initiatives and back Stripe to the hill. But someone's got to pay for this at scale. And so our view actually was like, if you're going to make a stepping stone in terms of deployment to get to the point where you have megaton and gigaton scale projects of carbon dioxide removal via direct air capture and geological injection, for example, or mineralization, which we consider to be the gold standard in this space, is that you need opportunities to deploy systems. Like, this is hardware. It's like, it's not necessarily like software where, if you get the right combination of your code in place, then things will work out. This is a little bit like nature doesn't really care about your feelings, and the unknown unknowns are so much larger than you could possibly predict. And so, to a large degree, you need opportunities to mess things up, to deploy systems, to find out how it works, and you need someone to pay for that to be the case. And so there's two situations here. You can either go, I need a bank to project finance something which has never been proven, has like a stupid amount of risk associated with it, or I could sell CO2 to somebody that already buys it and the pricing's established. And the question for us is to figure out how we make something that's relevant for their use case so that we can make the technology fitter and fitter. So for us, we were like, actually, CO2 utilization is a really interesting aspect of the market at this moment in time. CO2 is like worth $10 billion. It's only going to grow. And the more we looked into the CO2 market, we were just like, this just makes so much sense, just like a scaling exercise over the next couple of years to then get to massive deployments in the future.
And so who are those buyers that you're targeting first?
We're particularly interested in like building materials. So, in building materials, you have like this dual ability to sell the CO2 to somebody that uses large volumes of it. But also, the CO2 is just inherently locked in a building material. It's like geological injection, but you're making houses. So what you can do is say, it has this nice fuel factor to it as well. And you go, not only have you removed CO2 from the atmosphere, it's going to make somebody's house because you make building blocks or roads out of it. So you can help make the world around us a better place. And I think this is like, CO2 utilization gets like a relatively bad rap in the space because obviously there's a strong focus on removals, and we completely agree with that. Decarbonization is important. Removals are really important. Like, it's aligned with, so we're completely aligned with like IPCC and the IEA guidelines. But fundamentally, like, if you have access to carbon in the atmosphere and you can use it at a relatively good price point and you can turn it into things, it's never been the case that we don't know what to do with CO2. We've known what to do with CO2 to make fuels, chemicals, pharmaceuticals, building materials, you name it, we can probably turn CO2 into it. I think people are making like yoga mats and carpets out of CO2 at this moment in time, right? So like our imagination of what we're able to do with CO2 is like almost limitless. The one thing we lack is like a reliable access to a sustainable source of CO2. And so tangential to this idea that, CO2 is pooling all around us in the atmosphere, like industries that could use CO2 can't get enough of the stuff because there is no access between the atmosphere and those industries. So if you basically just unlock that supply chain, then you have the opportunity to fundamentally revolutionize or change our relationship with carbon, because we can make all the things we need in our world out of carbon dioxide. We just can't access enough of the carbon dioxide. And if you change that situation, then we don't have to make all these things out of fossil fuels. We can actually make it in a sustainable, either circular or actually completely carbon negative way. So that's actually the large term vision of Mission Zero. It's not just about saying we fundamentally want to remove CO2. It's about, we want to fundamentally enable industries to readdress society's relationship with carbon. I think it's sort of tagline you use constantly, but like, atmospheric carbon is probably the one resource on the planet that we can use and use and use as much as we want of over the next 10, 50, 100 years. And things will only get better on the planet. It's the only resource that I can think of that displays this relationship where you have economic and environmental incentives aligned, whereas that doesn't tend to be the case anywhere else.
Yeah, I keep citing this without remembering who said it, but I was listening to a podcast and it was like the most optimistic take I've ever heard, which was that they thought the bigger problem that we were going to have by the end of the century was actually that we wouldn't have enough CO2 in the atmosphere. instead of having too much CO2 in the atmosphere. Do you see a path to that world? Is that even like close to realistic?
I think in most scenarios, we're talking about direct air capture, dealing with something like, I think something up to like 10 gigatons of CO2 per year by 2050. That's the scale of what it needs to achieve. And given the largest projects at this moment in time are on sort of like 4,000 tons a year, I think next year will be 40,000 tons a year. After that, will be a 500,000 ton plant. There's a lot of work to do. Like, it's almost like there's a large amount of proof points that need to be realized in by 2030 for this industry to take off in the way it needs to. But I'm sort of we have this like internal joke at Mission Zero. It's like, stop big DAC. You know, it's like, you're gonna have to pay us to turn the DAC machines off because we'll start an ice age. Like, you truly don't believe that. I sort of think a lot of people starting these companies and running them, and the reason that we're in it is because if we're all squabbling over the amount of CO2 in the atmosphere, and we've kind of done our job, we can go home in a way.
Yeah.
So, you know, I think the one thing I'll end on this bit is, like, you know, the other day, over Unity and fusion ignition got announced, right? And our view or conception of what the future looks like is always basically just wrong. Like, it's probably going to be better than we think it is. Every projection of renewable growth in terms of electricity for the past 20 years has been conservative, even when they thought it was like very liberal. You know, whilst our predictions of what the future will look like in terms of, we think we'll have this installed amount of direct air capture capacity by this time, is probably incorrect, because it doesn't belie any of the accelerating facts in terms of scientific breakthroughs, changes in regulations and policies, desperation just from like climate change getting really bad. So I am optimistic. It's still going to be hard, but I think it's entirely doable. So yeah.
When I hear numbers like the, 4,000 tons now, 40,000 tons next year, maybe 500,000 tons the year after that, these like order of magnitude increases, where I was going was kind of those exponential curves that you're talking about in the other areas. Like solar is kind of the prime example right now. Does direct air capture benefit from the same kind of experience curves as maybe solar does? Or is it just that people are now pouring resources into it because the supply chain is getting established and all of that?
I think it's like a mix of the two. And so what I'd say is, yes, these experience and learning curves will like play a massive role in bringing the cost of direct air capture down. I think it's realistic that you will see really cheap direct air capture by 2030. I think it's realistic you'll be sub $200 a ton by 2030. I wouldn't be surprised if someone came along and made it even cheaper than that. So I think a kind of conception that all of a sudden this is just too expensive for too long will be wrong, in the same way that, fusion was 50 years ago until the day that it wasn't, right? So there's an element here of, we just need to get deployments on the ground, and how that's supported is like a really important thing to get right. But it's just a question of getting on the ground and deploying, and actually the learning rates are pretty quick. Supply chains, yes, supply chains are going to be constrained, and particularly when you look at a lot of the technologies there. And Mission Zero probably falls into this bucket as well, in that, like, to get off the ground quickly, you're using off-the-shelf technologies or known processes where you have a high degree of confidence in them, and that allows you to navigate those technical valleys of death, so to speak. But then you're just creating like another valley of death in your future, where you go, if, for example, in Mission Zero, we're using a water purification technology to regenerate our CO2. When we get to scale, are we going to be competing with projects that actually, are we going to be taking supply chain and resources away from air purification needs? And so for us, is when do we do like the vertical integration question? I think for us, like, become sooner rather than later, just because it actually represents a really big opportunity. But at the same time, if you then have all these companies setting up their own established supply chains and manufacturing methods for like technologies which have a high degree of versatility to them as well, you have this opportunity to create like high degrees of abundance. So let's say we set up our own, in the regeneration side of our technology, we use a technology called electrodialysis. It's a membrane approach. It's used to desalt soy sauce and pharmaceuticals and process dairy every day. Like, it's kind of technology where it's all patented it. The patent expired 25 years later, and it's been used for another 20 years. So like, the uniqueness for us is like how we're using it. It's not necessarily we came up with electrodialysis. It's the unique implementation of it or technology. But let's say we start getting towards megaton or even gigaton scale, like, we're going to find supply chains, lead times for coming online will be massively impacted. And so, probably going to have to build supply chains ourselves and manufacturing capability ourselves. But it turns out the membranes are useful for things like lithium refining, or continuing to ensure food security as well. So I think what we'll find is like the function of building of these supply chains, whilst they might be viewed as, what's the word? A constraint in the future, will actually will create like opportunities in other spaces just by the very fact that they have this versatility. So
I want to dive more into
Yeah.
the how you think about kind of maybe doing the vertical integration. To get there, maybe to start, could you explain to a layman like me how the process works today, just so we can understand even where there are opportunities later for vertical integration?
Yeah, of course. At a very high level, like direct air capture is quite a simple process. So you capture CO2 in a medium and then you regenerate the CO2 from that medium. And so the way we capture CO2, the medium we use is basically water. It's a solvent, there's a majority water. We have a small percentage by weight of a carbon capture agent. This is an off-the-shelf commodity chemical. It's in Febreze in the US. So, like it's something that's mass produced at scale. And actually the chemistry of it isn't specific to that molecule. So we could use a variety of different capture agents. There's a couple of salts in there. It's a very, very simple, there's a couple of other things as well, but it's a very simple like solvent chemistry essentially. And then what we're able to do is regenerate it using this water purification technology. And so think of it as we have a medium in which CO2 can either be captured or regenerated. That's the solvent. Simply have like two kind of like process infrastructures or like technology pieces which enable that capture regeneration. And so on the first side, we use basically active cooling towers, which are used in power generation every day. They've been used for years and years, like decades. We wouldn't be having this call right now. We'd have like stable electricity or internet if there wasn't cooling towers that work day in, day out on a massive scale. So the ability to leverage those supply chains and that manufacturing expertise. And like I said, this kind of thing where the expertise has been around for like 5 decades. It's not like something where someone's just set up 5 years ago. So it's kind of thing that has reliability. I can come into the vertical integration on that in a minute. And then once you capture CO2 immediately, the way that it works basically is you have a fan, you have a packing material on the inside of basically, and then you trickle water or the solvent over this packing material, create the high surface area thin film, and perpendicular to the flow. So imagine the flow is coming down. You then have this perpendicular flow, and then we kind of create like a fizzy drink, like a beverage. We store CO2 the same way that CO2 is stored in a can of Coke. It's just that the additive allows us to store it at atmospheric pressure or temperature rather than needing to be stored under pressure, for example. And so because it's stored in this kind of metastable state, it's stabilized long enough for us to take it into the regeneration process. And then the regeneration process, we pass it through this water purification technology, which is again off the shelf, it's used in desalination plants all around the world. It's used in semiconductor fabs. It's used in power generation. It's used in food processing. Like it's a pretty well understood off the shelf technology that has the same amount of decades of experience and know-how in the market and supply chains and manufacturers behind it. And what we're able to do using that is unique to the solvent chemistry we come up with. We can regenerate the solvent using only electricity. And then we also regenerate the CO2 from the solvent. And it comes out about 98% more pure. The other 2% is humidity. So it's not a large stretch to refine it to commodity grade. It's just relevant to food and beverage straight away. You can liquefy, compress. It's very easy to integrate. And then once you regenerate the solvent in that process, you can then continuously put it back through the first step. So you're continuously capturing CO2 on one side and then continuously regenerating it on the other side. Now, most DAC technologies in their instance are, and I'll get onto the thing I was supposed to answer here, which is like the vertical integration where the cost reduction pathways are. But most DAC technologies in that instance are essentially batch technologies. So think of it like a capacitor or a battery. You charge it with CO2 and then you have to expend a large amount of energy discharging the CO2 from that medium. Because we're kind of like not switching between temperature environments or humidity or pressure swings or anything like this. We're not going from extreme to extreme. We can operate in a radically different way, essentially. In terms of the vertical integration and cost reduction, I think this will be like a general thing that most of the DAC technologies will find is that the key components of the technology, as they start going in the supply chains and somebody else's margin, if I just made it myself, probably I'll make it actually better for my specific needs and it would just be cheaper. But I think one of the main things is most processes use large amount of fans. processes a lot amount of electricity in terms of moving all the air through their material, whether it's a solvent or a solid packed bed, which is common in other technology types. So actually, the supply chain and growth of fans is like one thing that could be quite interesting. At least a while process, like the blowing lots of air, you need a lot of fans. But specific to our process, like we can give an example, like the packing material internally, which is used in cooling towers, is like it's basically just crinkled PVC. It's really simple. But they charge you through the nose for it. So for you to be able to make your own design and have your own production capability on side, then you'd massively reduce one of the main core constraints and cost centers within that. Then on the membrane side, the ability to make your own membranes and make them on the timelines and sort of size that you need, rather than for your actual deployment, means that instead of like paying like very high prices for what might be like several meters squared in membrane, actually you're talking maybe a 10 times reduction in the total cost essentially of the membranes that you're using. If you were to just, not even with any innovation potential in the membrane design itself, if you were literally just to say, I am going to put the capex down to make my own membranes now, you would realize a 10 times reduction in the cost per meter squared. And probably you'd have like megatons of CO2 regeneration capability online available to you within a year. So you probably have more membrane than you know what to do. If we did that over 2023, we have more membrane than we knew what to do with. Let's put it that way. We probably then, and this is the kind of abundance thing I was referencing earlier, it's like, I would probably then just start selling it to the market because people are also membranes in different industries. So, using off the shelf materials is great because it allows fast deployment, but you're always going to pay someone else's margins. So if you can bring, probably not the whole vertical integration question, at least in Mission Zero's case, immediately in-house, but there's probably core technology components where you're like, it makes sense for us to own, could also like Karl Marx, the means of production.
When you look out 10 years in your model or whatever, once you're vertically integrated, what does vertically integrating do to the cost per ton versus kind of using off the shelf materials today?
It's massive, really. So, I mean, one thing to say about our cost structure is that a large part of our cost comes from the fact that we're electric only. And so I think our CapEx, OpEx is roughly 2 to 1. So aligning ourselves with cheap sources of electricity is like one of the key levers in our roadmap over the next 10 years to reduce costs. But in terms of like bringing down costs, like vertical integration is huge. And it also, I think it's realistic. We're projecting that we should be able to get to less than $100 a ton by 2030 as a function for vertical integration. I think one of the main things here is like what it enables as well. So at least the form factor of our technology is, the idea is you have an air compacting unit when you capture CO2 and then a regeneration unit where you get the CO2 back. And those both fit within a 40-foot shipping container. And so we think there's an element of like building larger and larger plants in the way that you view like chemical plants of the old way of doing things. But ultimately, I'd take an example of like the ITER fusion project where I can't even remember how many billions it's over schedule in terms of time and cost and all these kinds of things. Like you go bigger and bigger, like the lead times and the ambiguity get bigger and bigger. And if you have one piece that doesn't work, which actually happened recently in the ITER project, you have to send it back, you're delayed by 24 months, like it's probably never going to happen. But if you have this ability to pump out capability constantly and you go, a unit is capable of say 1,000 tons a year, we produce enough for say 13 megatons a year from one factory, for instance, then you're just continuously pumping this since you get this cumulative growth of CO2 removal capability. So one system might be very small, the ability to produce like 500 of them a week, for example, something in the same Tesla produces cars, means that, you can create these buffer zones, and this is to like our commercial thesis, but you can create these like buffer zones, you can deploy whole capabilities to open up new markets if you wanted to. You can deploy an entire DAX capability on a ship within 3 weeks. Like there's all these like really interesting things you can do when it fits within 40-foot shipping containers and you're continuously producing them. And so it gets around this kind of traditional thinking of like the thing we're building is this size, it costs this much. And if you want to build a bigger one, your costs will just go like this. From this point of perspective, with this kind of modular mass production perspective, like costs come down and you have this incredible flexibility that will actually, we think, is what enables you to scale the technology the way they need to actually get to like a gigaton scale by 2050.
Would you operate all these and have staff on site, or is there a world in which I move out of Brooklyn to somewhere where I actually have space in my backyard and I can buy a couple of these shipping containers from you and do it myself in my backyard?
I think the way that the way that we're envisaging this probably initially is that the technology is basically autonomous. So the way that we want it to work is that it actually requires very little engagement from anyone. You know, it goes back to like the commercial scoping you were doing, but when we were looking at like why someone would buy this, one of the main things was like it sits in the corner, it provides CO2 as it's needed, but it doesn't get in our way. Like it's not a headache for us, it's a value add, and that value add is like being dependable and reliable. So probably what we think it's a case of like getting a deployment set up, 3 to 6 months of operation, being on the ground, learning, tweaking the system, ensuring that it's got a good baseline, and then walking away from it, leaving it to deal with itself. We provide training to staff on site who are using the technology. So if this is implemented with the customer, if it's just us using ourselves, then it'd be a similar thing. But obviously, like if something goes wrong, we can just respond to it immediately. If it gets cheap enough, maybe people would want to like buy them themselves. But I think there's a certain element here of like, what do you do with the CO2 once you've got it? And so unless there's like a really good articulation of like how you're using the CO2, I mean, I'd be more than happy to sell you a system of any size that you'd like, but you're just going to be capturing CO2 and regenerating it back to the atmosphere. And so I think it's a question of like who you work with, what that use case is. Do you have a geological injection site? I mean, I could conceive of a kind of
don't,
like
unfortunately,
small modular
right now.
system to the to the point where you have like last mile delivery or collection of CO2 from people's houses. But I think for like the most leverage and biggest gain in terms of like removing CO2 from the atmosphere, there's going to be a certain element of centralization in what that looks like.
Yeah, so maybe in 100 years, I'll be operating my soda stream just by pulling CO2 out of the air. But until that point, it makes sense that
You
if
mentioned
you're
the
making
stream.
soda,
We have this joke in the company where it's like, we're going to build DAC soda. And I keep saying to my CTO, DAC soda is not going to be a thing, but maybe it will. So who knows?
well, sign me up for the
Just
first order if that ever becomes
Okay,
becomes
will
a thing.
do. Will do.
So one of the things that you said in there, in terms of just kind of how the electricity component of this and the energy consumption component of this, I know one of the things about Mission Zero is that by using less energy, you can deliver kind of cheaper direct air capture. One of my kind of big introductions to the space is just reading Casey Hanmer's stuff from Terraform Industries on just the abundance of solar power and how that's going to make it such that like it doesn't even matter how much electricity you use. Where do you fall on that spectrum where like the process should be energy efficient, or like just trust that solar curve that we talked about, and at some point it'll just be so cheap that who cares?
I think it's probably both. So, I mean, because of the deployment strategy that we have, the focus will always be for us on making this as energy efficient as possible, because electricity is a really pure form of energy comparative to like heat. Often you're converting electricity into heat in some instances here, which is some TAC technologies. It very much makes sense to us to like use it in its purest form, so you're not wasting or turning essentially a large amount of things to heat, whether it's directly or indirectly. But you're right. Like I think it's a function of like we should aim to be as energy efficient as possible, so that when solar is so abundant that it's not even funny and that it's just like there all the time, then that just means it's easier to scale, and it means it's easier to like deploy it, and actually we can remove even more carbon dioxide. So there's a little bit of Jared's paradox around it in my mind. Like let's stay efficient so that when things become incredibly abundant, we can just do more. The process itself, I mean, I probably didn't touch on this so much as I was explaining earlier, is that it works the same way that biology processes CO2. So it stores its bicarbonate ions and protons. And the electrical focus, with that realization in mind that, it's a very pure form of energy, is that you want to utilize as little of it as possible. And the way that we capture and regenerate the CO2 means that, we can be very frugal with the amount of electricity we use. And so, yeah, it just means the capture, the regeneration efficiency is very high. It's very close to what you need for industrial integration. And it's the one thing you can guarantee on site is just electricity. You can't guarantee any form of waste heat. You can't guarantee, other things that other technologies might use. You can turn up to any industrial site and guarantee electricity connection. So, and as grids decarbonize, Grid electricity in the UK for us means that our process is 80% net negative. And then if we align ourselves with renewables, which we will be in 24, then it's 99% net negative. So, it is one of these technologies where if you're just using electricity and you're avoiding heat, which will often bake emissions into the process, you have this opportunity to actually exert this really high leverage in terms of the amount of CO2 that you're removing. Let's scale renewables. Let's use all the free, curtailment. Let's get really cheap solar. And let's just be really frugal in the amount we use as well so that we can do more with it, would be my
Amen.
general
Yeah.
throwaway comment.
I would love for everybody listening to this to really feel like they're one, mission zero experts, and then two, direct air capture experts more generally. And so want to dive in as deep as we possibly can on the numbers of what this looks like. And we can do today, 5 years from now, kind of at maturity, maybe a comparison of both, but what the kind of unit economics look like and what the business looks like in a very specific way in terms of you mentioned 2/3 goes into CapEx. Like, what are the CapEx costs? What are the OpEx costs? And then who's buying? How much are they paying per ton of carbon? How much is something like an advanced market commitment supporting this right now? How much is it someone saying, I actually need CO2, and what are they paying? So just what's like the whole business in a nutshell?
Initially, we're looking at deployments where, so one thing to say is I would characterize this in two ways. One is carbon credit removals or credit sales, essentially. And so that's the pre-purchase agreement that we reached with Stripe as of 2021, and we're delivering on that in 2023. And the other side is basically CO2 sales or CapEx sales aligned with providing CO2 to somebody. And so there will be overlap where you can achieve those in some situations, like this carbon negative building aggregates project that we're doing in 23. But I would segment them basically along those two lines. Now, on the credit side, I think we can all agree on the scale of the problem. It's going to be really, really it's going to be really big. Yeah, there's a lot of work to be done to get to that point where the value is so overwhelming and huge. And there's a lot that companies need to do to scale to get to that point to even realize the potential of it. So I think, you could buy direct air capture on the open market. Let's say Climeworks, for example, one of the big three and the sort of first wave of DAP companies. You can buy it from them on their websites at the time. I think I haven't checked their prices, so please don't sue me, Climeworks. But it's coming in roughly about €1,000 a ton. So like this, if you're like an individual member of the public buying carbon removal from them, the prices will be slightly cheaper if you are, for example, like a corporate buyer of large amounts. And, that makes sense from their perspective. I don't know exactly what the cost of capture are at this moment in time, but it's, there was a Stripe did buy removal from them. And I think it was like $775 a ton or something like this. So we're in that kind of ballpark. It's high hundreds, getting towards 1,000. That's kind of where we are at this moment in time. Company called Carbon Engineering comes along, deploys a 500,000 ton per year system in 24, I think, or 25. And has sold removal to Airbus, for example, for on the order of $250 to $300 a ton, for example, something like this. So, this is what I mean is there will be these kinds of if that works, you're kind of possibly getting there. It's, by 2030, this is realistic. It's possible. And then ultimately, I think from a kind of removals perspective on the price, it has to come in about $200 a ton. There's a kind of dark part of me that goes things will become so dire climate change wise in terms of food security and all these kinds of things that governments will start to make direct payments for carbon removal, because from a security perspective, from a biodiversity security perspective, we just need them, right?
Yeah.
So there's a little bit in my mind thinks something like that might happen. But even if you get to a kind of established voluntary carbon credit market, $200 a ton is the minimum price point in my understanding. There's a really good report from Goldman Sachs on Carbonomics, I think, that outlines that basically. So once you start getting to $200 a ton and below, economic, this starts to become something that corporates are very happy to buy into. And it makes a lot of sense.
The corporates who are buying now at $1,000, at $775, whatever it is, why are they doing that? Frontier, I understand is, set up to do that. But if you're a company outside of that, that's buying the highest quality direct air capture credits right now, removal credits right now, why are you doing that versus buying reforestation credits or farm credit, something else that is cheaper, but you can also say, I bought all these credits and look how, ESG we're being and all of that.
I think it's interesting, and what I don't want to do is necessarily seriously might annoy one of my first customers, right? I think it's interesting that the main buyers of large amounts of carbon removal upfront are Shopify and Stripe, right? The two leaders in this space who like set standards and are setting the rules as well. And I'm not just setting like average rules, like they're good rules to play by. Like it enables something really interesting in the future. This focus on durability, permanence, like standards around verification, all this kind of stuff. It's really good stuff. But if you look at them, they're payment companies. And what they want to do is probably embed carbon removal into their products. And I think Shopify said this themselves. They're like, we went out to find it and we couldn't find it. It didn't exist. That's an element of like, we have to grow it ourselves. And if you look at the amount of money, like the amount of money that these companies have put into this, apart from Frontier, which is like an almost $1 billion fund, and who knows what happens to it in the future when it gets larger or it's not spin out. And you have other AMCs starting up. I think I can't remember the name of it now, but it's a really big one. You've got, even at the country level, countries starting to buy into this idea. It's still a relatively small amount of capital to put into projects that are going to be operating at megaton or gigaton scale. It's very much just focused on like, we'll take a relatively high risk. Think of it almost as like venture capital, in that like, we're going to take a very high risk. Who knows what pays off? We'll take a portfolio approach. Some will die. Some will do really well. The ones that do really well, we're the first people that enable them. Like they're going to love us. So why wouldn't we work with them? And so I think it's really good business, actually. I think this idea that it's like, you don't have any surety on the outcome of it is kind of belying the fact that it's like, you might create an entirely new market and you might catalyze an entire new industry and you'll be the ones at the beginning of it and you own that. And so I'd say to anyone thinking about it in this space, is like, yeah, it seems pretty risky, but it actually like pays off. The risk reward profile is like, it's insane. There's no other way of putting it. I'm not financially savvy enough. I'm a scientist, not financially savvy enough to couch this in anything like adequately, but I would say that it's pretty big.
How many tons is in a gigaton? And then we're talking even $200 per ton. It's just a massive, massive, massive market.
Yeah. It's a gigaton is 1 billion tons. And so you're looking at 200 billion to remove a gigaton of CO2. But there's like this interesting like back of the envelope calculation you can do where it's like, one, we have these numbers that are thrown around about the cost of fixing climate change. And if we don't, versus like actively doing something, which might cost in the case of a gigaton, like 200 billion, for example, versus just letting climate change play out and fix all the pieces that go wrong essentially and just accept it. One, we haven't actually changed anything. Things have just got worse. And probably it's in the order of trillions of dollars more than anything else. And so it might sound like a lot of money. It's just flippant for me to say like, yeah, it's only $200 billion. But actually like it's a sum of money on the scale of like the global economy where it's like, it's a pretty good investment. Like it's a pretty good one.
It's funny how similar it is to just healthcare, right? Like the US spends something like 17% of GDP on healthcare because we don't spend enough on preventative care. And it would be way cheaper if we just spent money on preventative care.
Fixing climate change via direct air capture, a load of other carbon removal methods and reforestation is like really good climate preventative healthcare. That's the way you should think about it. I think that's perfect. I really like that. I'm going to use that in the future. Thank you.
You're welcome. I'm glad you got something from this. I guess on the other side then, so that side makes more sense to me now. What are people buying CO2 to use it for? Like, what are they paying to use the CO2?
So the largest usage of CO2 at the moment is food and beverage. It's basically carbonating drinks. So putting in fizzy drinks or driving beer lines or these kinds of things. There is a growing subset of users who are making things like building materials. There's a load of startups focused on this area as well. Turning things to plastics, making chemicals out of them, all this kind of stuff. And so, it's probably, I think that the first thing I'd want to say here is like when we started looking at the CO2 market, we thought this could be really interesting, is that there's a couple of really interesting like integration questions to be figured out here. So one, if you look at the way the CO2 market is structured, at least across Europe and UK, and this will largely be the case in a variety of other geographies, is that CO2 is sourced as a waste byproduct from the ammonia industry. So you take natural gas, you split it to make hydrogen, the leftover oxygen and carbon makes CO2. And instead of emitting that to the atmosphere directly, the ammonia plants basically purify it, bottle it, and sell it to merchants who then sell it on to you in the form of like your can of Coke or something like this. And so you open a can of Coke, apologies for anyone that I've ruined a can of Coke, for example, is that, when you open a fizzy drink, what you're really doing is just emitting CO2 that's been delayed from burning of natural gas. That's usually where the CO2 has come from. And so you then look at like the way the market's structured. So none of this CO2 is made for the people that actually want to buy CO2, because it's like constrained and tied to essentially the price of the natural gas markets. So let's take an example. Most ammonia plants go down for a retrofit over the summer, and then if the natural gas price gets too expensive as well, they'll shut the plant down because it doesn't make any economic sense to make ammonia. That's all of a sudden the entire CO2 supply chain just goes into shock. So there is no supply that's guaranteed. Price fluctuations are crazy. You could be the largest buyer of CO2 in the UK or Europe or worldwide, and you might just have force majeure placed on you, and your prices might increase 10 times in the space of like a week, and they will stay like that for a year. And so, I think you can look it up. There's probably a story that happens every couple of months where BBC News or something like this was like CO2 supply chains like dry up and we're 3 days away from beer lines running out. And so it's a really sad story, right? Because still wants that and wants to run out of beer.
No.
But, for us then we were like, well, actually direct air capture solves a lot of these problems. Often in commodity markets, it's this view that it's a race to the bottom in terms of price, but you can actually stratify commodity markets based on risk. So if you go, actually, like the risk of using this commodity in its current format is that it can't guarantee supply, price might 10 times increase without me having any control over it. And if I want to double my business or my process, there is no ability for me to actually get more of the CO2. So direct air capture is one of those technologies like, I can tell you over a 10 or 20 year timeline what the price is going to be. It might even get cheaper. If you want to double supply, that's just a question of installing more units rather than saying, sorry, an ammonia plant went down for a retrofit and there is no supply in the market. And fundamentally, like we're making the CO2 for you. We're not, going, oh, great, you can have the scraps of the waste that we produced. And we've made this specifically for you. So you fundamentally reconnect that supply-demand relationship. And so you basically, the market's just, in our view, just waiting to be like revolutionized. And so I haven't had a single conversation with someone that buys CO2 where they're like, I love the way that I get CO2. It's like the biggest problem in their entire business. So if we, we basically got buy-in from like one of the largest users of CO2 in the UK before we'd even formed the company, because they were so frustrated with the way they got CO2. They're like, so you're not even a company yet? We're like, no. And they're like, if you can build this, we'd happily buy it. So, we felt like we found like a really strong market fit quite early on, and have just been validating and building on that essentially. And that's what we view as like these implementations in the commodity market where you might have overlapping with removals. That's cool. That's nice. But fundamentally, you can sell a product into $1 billion market where the price is established, and you can segment the commodity market by risk and solve those risks. So not only like solving like supply chain issues for companies, you're also just like making their lives easier. And that's always going to be like a winner. In terms of price, let me give you an example of the kind of fluctuations that occur. So prior to the pandemic, maybe like spring 2020, largest users are paying like 100, 200 pounds a ton CO2, for example, something like this. Pandemic happens, and supply chain risks and natural gas, and price goes up tenfold. And over really busy periods as well, you might be paying like £1,000 a ton, something stupid like this, and the product hasn't changed, and you have zero control over it. And even if that's the quoted price they've given you, they might not turn up at site. So you might have force majeure placed on you, but in the even worst case, you might just not have someone turn up with a tag on you up with CO2. And if you're a company that relies on CO2 to either drive beer lines or, to, for example, building aggregates, like it's fundamental to your process. If you don't have the input, you have to shut down. And so from a continuity perspective, you're also just able to say to these companies, you don't have to worry about continuity. We've got you and we're here for you. That's why we exist. And so it's basic and frictionless. You can walk in and go, here's the product. Here's how it's going to work. And they go, oh, I don't have to worry about these things. It's great. I can do other things. So
I also can't imagine really a more depressing situation than the climate going to shit while we're out of beer because we can't produce enough
Yeah,
CO2 to make
exactly,
it
right?
work. If it's going to go to
Exactly.
shit, we got to drink.
Exactly. It's miserable. Like, so we view it as like a humanitarian effort as well to ensure there's enough beer for everyone on the planet.
No, you're doing God's work. I have a question, which I think will be useful. Like I've loved, and I'm probably just naming all like the intro to climate people here, but like the whole Chris Aka method of just being like, we're gonna make a
Yeah.
shitload of money in climate. Like
Yeah.
this is not about like a do-gooder thing. We're making a shitload of money. How big do you think Mission Zero can get? Like, what kind of outcome are you aiming for here?
I want us to be moving gigatons of CO2 by 2050. I want to be like responsible for like a certain percentage of climate change. I think that's how big DAC has to be. Like, I think it's out of the 51 gigatons of CO2 we need to remove every year by 2050. Like it's responsible for 10 of them. It's a fifth. Like it's a lot. And so if you consider there's going to be a couple of companies doing this, like probably a couple of companies who win in the space. And again, I don't think it's this kind of thing where there'll be one outright winner. I think you'll have like some kind of specialization, niches, use cases where they make sense versus others where they don't. It's going to be the case that a couple of companies are removing about 10 gigatons a year of CO2. So even if you just do some math, say we're 1 of 5, that's like 2 gigatons by 2050. That's crazy. But I think we have to dream that big. I don't think we have any other option. So, and I'd love to see like, again, align this kind of idea of like, we can view all these problems that are coming up to us over the next 30 years as like, we could just stand there and panic and freeze, and we go, all right. Or this is like a huge opportunity. Like I like this idea of like, we have access to the largest like strategic carbon reserve on the planet. And the more we use it, things only get better. Like that's the only resource I can think that displays that relationship. So in the same way we go, well, we're going to have to reduce loads of membranes. So why don't we just make water purification cheaper as well by like a nice byproduct? Why don't we make cooling towers even more efficient so that, they lose less water, for example. And so you make energy generation even cheaper. Like there's all these kinds of things where you go, cool. Probably on our technology development roadmap, like there are going to be tangentials which are positive in nature as well, but other aspects of fixing climate change. And we'll just make the human condition better generally. So yeah, I think in this game you have to be optimistic. Don't bother otherwise, because the dream is big. And there's a lot of people who are willing to dream with you as well. So just come in and get involved. But this is like planetary level, like it's basically terraforming that we're going to have to do over the next 30 years. So, small ambitions don't apply.
So you anticipated my last question. Normally I ask people what the world looks like in a decade. If they succeed, I'm going to go with the 2050 timeframe. You touched on it earlier. You touched about this like kind of unpredictable abundance and like compounding different things going well.
Yeah.
But I'm going to put you on the spot and ask you like what that world looks like. If you could just like dream out to 2050, what does the world look like if you're as successful as possible and the kind of the industry is as successful as possible?
We, house ourselves in and the infrastructure that makes our cities is like a massive carbon sink. So I'd want to see like CO2 being injected to concrete and being injected into aggregates to make everything around our world so that, there's more built things at this moment in time on the planet than we've made than there are biological things by mass, right? That's ridiculous. But we're only going to keep building cities. So why don't we just like view them as a massive carbon sink? I'd want to be taking like paracetamol made from CO2. Like, I'd want to like fly on a plane to Australia on fuel made from CO2. Like, I'd fundamentally want to see like a readdressing of our relationship with carbon, because I believe that's fundamentally possible. If our whole thesis on like the availability of renewables, cheap electricity, new technologies, and who knows what's going to happen over the next 30 years. Like we just got fusion a couple of days ago. Like who knows what's going to happen? Like the world is going to be crazy. Like our conception of what it's going to look like is insane. So probably even my conception of I'd love to see us like turning buildings into carbon sources and flying on carbon neutral fuels, taking paracetamol made from CO2 is probably really boring and mundane. So who knows?
Man, I love it. That is the perfect place to end. Nick, thank you so much for doing this. I'm obviously going to be rooting you on and can't wait to see you get to that couple gigatons a year.
Thanks, Becky. I really enjoyed it. Thank you so much for having me.